In this video, we're going to look at an alternating series and determining when those series are convergent and when they're divergent. Now here's an example of a fairly common alternating series. Right? This is a very common example. You'll probably see it in textbooks and any other materials you look for online. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and continuing so on. Right? And here I've written it as an infinite series from 1 to infinity of -1 to the n plus 1 times 1 over n. Now, the reason this is an alternating series is because the signs are alternating every time you increase the index. So we have a +1, -1/2, +1/3, negative, positive, negative, positive, and that pattern has to continue throughout the entire series. That's what makes it alternating. The kind of giveaway when in series notation that it's an alternating series is this -1 raised to a power. However, we'll go through when that's not the case, but that's kind of a giveaway for you're working with an alternating series. Another way to just kind of easily tell is write out the first few terms in the series, and you'll notice these signs switching throughout. And if they are, then you're dealing with an alternating series. So now let's go through when those series are convergent and when they're divergent. Okay, so here's the alternating series test. If you have an alternating series, get it into the form -1 to the n power times some function, some expression, b of n. Now, you need to meet two conditions in order for this series to converge. If it fails either one of these conditions, it will diverge. Now, be very careful when learning all these different kinds of tests, because some tests, like the alternating series test, will be, a certain set of conditions. If met, this series will converge, and if it doesn't meet those conditions, it will diverge. Now, there are other tests that tell you that they converge, or they give you no information at all. And I'll have separate videos on those. So just remember, for the alternating series test, it either converges, and if it fails these conditions, it will diverge. Now, here are the two conditions. This b sub n plus 1 must be less than or equal to b sub n. What that means is at a certain point, your function this b of n needs to be decreasing. Now, it doesn't need to be decreasing forever. There are plenty of times where it has to be eventually decreasing. An example of that would be if you somehow had a sequence that was 1, 2, 3, 4, 5, 6, and after 6, it started going 0, -1, -2, -3, and went like that until infinity, then that is something that qualifies as satisfying this condition. Okay? It's not that it has to be what's called monotone decreasing throughout the entire sequence. It has to be eventually decreasing. The other condition that it has to meet is that the limit of b of n as n approaches infinity must be 0. If it's 0, then you have a function, then you have a series that converges. If it fails either one of these, then it's divergent. Now, let's look at just a few examples. So, we'll start off right here with -1 to the n minus 1 over 7 plus 3n. So first, let's get into the form where it's -1 to some power times some other thing, okay? And all we have to do, it's still a series, and just, I'm not going to write the indexes, just keep in mind that these will carry over. -1 to the n minus 1 times 1 over 7 plus 3n. Now, my b of n I found to be 1 over 7 plus 3n. Now we have to check these two conditions for that b of n term. All right, so I think it's kind of simple to see that this function is increasing because your variable is in the denominator and it's causing your denominator to increase over time, making this overall fraction decrease over time. But here's kind of like a way to see it as an inequality. So I have to show that what b of n is and what b of n plus 1 is and their relationship to each other. So in general, b of n will always be 1 over 7 plus 3n, and b of n plus 1 will be 1 over 7 plus 3 times n plus 1. Multiplying this out, this ends up becoming a 1 over 7 plus 3n plus 3. And from there, we can see this denominator is clearly always going to be 3 more than this denominator, meaning this fraction must always be smaller than this fraction. Therefore, we've satisfied the first condition of b of n plus 1 is always less than b of n. Now, let's just grab a separate sheet of paper to look at the second condition, right? Which is the limit of, as n approaches infinity, of 1 over 7 plus 3n, it needs to equal 0. Now, I'm assuming you know how to take limits at this point. It should have been either in a previous course or done much, much earlier in the semester or school year. So from here, I think it's kind of simple to say that this fraction gets smaller and smaller over time, meaning that this limit should end up equaling 0. So that condition, the second condition, is also met. Meaning this particular series converges. Now let's look at the next example of this. So we have the infinite series from 1 to infinity, 3 over negative n times 2n plus, times 2 to the n plus 6 to the n. Okay. Now notice it doesn't really matter what the exponent is as long as it's negative 1 to some exponent that has the variable that we're changing. So all I do is I take out the negative 1, and it ends up being 1 over negative 1 to the n that I take out. But I think it's kind of trivial to show 1 over negative 1 to the n is going to end up being the same thing as negative 1 to the n, right? You can convince yourself of this by writing out a few terms. So the way I end up splitting this, this is separate. The way I end up splitting this is a negative 1 to the n power multiplied by 3 over 2n plus 2 to the n plus 6 to the n. So my b of n term is 3 over 2 to the n plus 6 to the n. Now the first test, see whether it's decreasing over time. All right, and once again, I think that's, for this particular example, fairly simple, right? You can clearly see that if I just replace those two, 3 over 2 to the n plus 1 plus 6 over s to the n plus 1 should be greater or equal to, or should be less than or equal to your original. 3 over 2 to the n plus 6 over n plus 1. 6 to the n. Right, and the reason for this is 2 to the n plus 6 to the n is a smaller number than 2 to the n plus 1 plus 6 to the n plus 1. So it satisfies that first condition of being decreasing. Now let's check the second condition. So I'm going to grab a separate sheet, and 3 over 2n plus 6n. So we need the limit as n approaches infinity of 3 over 2 to the n plus 6 to the n. And this is another example where it's easy to see over time this thing decreases. Taking the limit of this, you end up with the limit equaling 0. So this satisfies both conditions, meaning that it must be convergent. So now let's look at some trickier examples that you might end up with. And I'm going to just grab a different marker. So here are a couple more examples of various sequences. Now, this is kind of something I mentioned earlier in the video. This first series, -1 to the 2n times 1 over n, it looks a lot similar to the series I had before. It's -1 to some exponent that has the variable in it times 1 over n. That's the 1 over n would be our b of n component. But this isn't actually an alternating series. You can write out the terms. This series would end up being 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, which is not an alternating series. The reason for that, this exponent, the 2n, is causing every exponent that's on the -1 to always be even. Right? And a similar thing can be seen if the exponent was 2n plus 1. These two, which you might see in other classes, especially if you're doing higher level math, 2n is the definition of what it means to be an even number. 2n plus 1 is the definition of what it means to be an odd number, as long as n is some integer. So when your exponent is always odd or your exponent's always even, you're always going to get a negative or a positive when on the -1. So this is actually not an alternating series. You need to use some other kind of test to determine convergence or divergence. So that's something to always look out for. This is not an alternating series. So it's always safe to just write out the first few terms just to make sure. Unless you are really familiar with being able to identify this number is always going to be even, meaning that's always going to end up being a positive one, no matter what. Now, this last example is one of the trickier things you're going to need to deal with. Okay, so so this is already separated out, my -1 to some exponent, and notice how this is not to the n or to the n plus 1 or n minus 1. It really doesn't matter, like I said before, as long as it's the variables in the exponent and it's causing this to change its sign every time with every increase of n. Okay, so here my b of n is -n over n plus 4. Now, the first condition isn't so easy to check, right? The second condition is easy enough. You have a bunch of limit techniques to figure out that the limit of this ends up being 0. The first condition requires a little more work because it's not immediately sure. It can't be immediately seen whether these terms will eventually decrease or eventually increase, right? The previous functions, the previous two examples, these were always decreasing, right? No matter what two numbers you picked, if you pick the numbers next to each other, the next one in your sequence is always going to be less than the term behind it. This isn't true for this one. And the way you kind of identify it's a trickier situation is your variable in both the numerator and the denominator, right? Different things are being done to it, and over time, they might act differently. The way you figure this out is something done fairly earlier. Finding critical points of this expression, of this function, right? It's back when you wanted to know between what points a function was increasing or decreasing. It's from that unit. There'll be a separate video on how to figure that out, and there are plenty of resources online. It's something you're kind of expected to know how to do by now. So finding your critical points would show that you have points at x equals 0, x equals -4, and x equals 4. Yeah, there we go. Now, -4 isn't even a term that's defined in your series because you start at 0, so that's not even something to look at. So currently we have the points 0 and 4. Now, a typical way to kind of figure this first condition out, a lot of people just pick two numbers that are next to each other, right? They'll make n equal to 2 and figure what that out is, n equal to 3, figure out what that is. By this definition, when n equals 3, this whole thing should be less. This b of n term should be less than when I made n equal to 2, which is not the case. Because if you took your critical points and did the specific test, you'd find out that it's increasing between 0 and 4. And it decreases from 4 to infinity. So although if you had done what the typical method for these are, you might determine that it's divergent, when in reality, since it's monotone decreasing after 4, it actually converges because it does satisfy this condition. And that is, unfortunately, I think it's the thing that comes up the most, and it's one of the trickier examples to deal with. Main takeaway from this video is alternating series. You want to check for changing signs, and always check the exponent on the -1 to make sure it's causing the -1 to change signs. Once you've separated out the -1 term from everything else, that everything else stuff becomes b of n. And you perform these two tests on it. You check these two conditions. If both conditions hold, your series converges. If not, your series diverges. If there are any questions, you can go ahead and drop something down in the comments. I'll try to reply. But that's pretty much it for this video. Good luck, guys.